Thank you very much. It's a pleasure to be here. So I was asked to speak a little bit about the data analysis we do for our understanding our gravitational wave sources and highlight a bit the latest results from the LIGO Virgo and Kaggle collaboration. So to get started, hopefully everyone is aware of this, and this is not a spoiler, but we have detected gravitational waves. As soon as Advanced LIGO began running back in 2015, or roughly an hour later, in fact, we got our first observation of gravitational waves. So this opened up our new way of doing astronomy. And here on the right is this first observation. And this is one of my favorite plots showing the data from the two LIGO detectors in Hanford and Livingston. You can see that they see the same signal in both. And this agrees very nicely with the predicted gravitational wave for a binary black hole merger. Now, while this plot is very lovely and very conclusively, I think, makes the argument that we have seen something, it's purposely designed to be simple. It's not how we actually do data analysis. The point of this was to show that you don't need to do fancy data analysis to see that there is a signal. You can just do things by eye, basically, with a little bit of filtering. So in the later parts of the talk, we're going to talk about how we actually do our analysis and how we came to the conclusion that this needs to be a binary black hole and what the significance of that measurement of the system is. So since our first detection back in 2015, they have become much more common. So at the end of our third observing run, they are almost an everyday occurrence. So here's a plot showing our cumulative number of detections here using a threshold of a probability of astrophysical origin of greater than 50%. So not necessarily all these candidates are going to be real signals, but they have better than even odds of being real. You can see that this growth in the number of detections has accelerated rapidly across observing runs as our detector network has got more sensitive. So the final observing runs here are O3A, O3B, about 6 months each, contribute the overwhelming majority, around about 80 or so of these candidates, despite the fact that O2 itself was a similar sort of length, O1 being 4 months, had only 4 detections. So we're getting lots of detections. The rate of detection is accelerating, and we're getting many more observations, and we can do all sorts of exciting science with these. Now, there are many potential gravitational wave sources. I'm going to limit myself to just talking about binary coalescences, because that's what we have seen so far. That was our first observation. This is what is consistent with all of these candidates to date. How do we know what they look like? Well, it's very thankful that we have an idea of what a binary merger looks like. So here's one of my favorite videos from the XSS collaboration showing a numerical relativity simulation, two black holes in a binary merging together. Here's a representation of the space-time in colors. The black hole orbits above. As the black holes orbit, they emit gravitational waves which carry energy and angular momentum. So the orbit shrinks, the orbit gets tighter, the black holes move faster, the gravitational wave emission gets stronger, the frequency of the gravitational waves go up. We have a runaway process. Now, this is a numerical relativity simulation, but of course there are many tools for calculating different parts of this orbit. Post-Newtonian calculations that inspire effective one-body formalism, perturbation theory for the merger and ring down. So putting all these together, we were able to get a good prediction for what these signals look like. And when we do data analysis, we're really comparing these observations, these predictions for what the signal should look like with our data. And it's from that we pick up the properties of the black holes. And so doing this for our candidates to date, we've come together with an image of what our observations are. Here's a cartoon showing these. It's a comparison of all our gravitational wave observations to date. So for each gravitational wave, there are 3 points on this plot representing the two initial components of the binary plus the mass of the final object of them. And also we have comparison with electromagnetic observations of neutron stars and black holes where the mass measurements are reliable to see what things look like in comparison. So you see we have a huge number of gravitational wave detections here. We have many black holes. We have already eclipsed the number of stellar mass black holes compared to the X-ray and other electromagnetic observations of black holes, despite them occurring over many decades, whereas gravitational waves is really just the last 5 years or so. And this really highlights how gravitational waves are perfect for these types of measurements, that are great for measuring these high mass systems and particularly for black holes and binaries. Looking at the lower mass end, we see gravitational waves here still lagging far behind what we do electromagnetically. With gravitational waves, we're much better at seeing higher mass systems as they emit stronger gravitational waves, so we preferentially observe those. So we're still behind on the electromagnetic side, but we are already seeing some interesting things. The distribution of masses of these systems isn't necessarily the same as electromagnetically, so we're maybe seeing different subpopulations here. Okay, so we have lots of detections. What can we do with these? All sorts of exciting science. So talks later in the schedule are going to go into these in more detail, but putting these together, we can infer the mass distribution of black holes, the spin distribution, redshift distribution, understand the astrophysical distribution of these objects. So this is taking out our gravitational wave selection effects and fitting for what the population is underneath. Here we have a plot showing various different mass models with parameters inferred from our observed populations. You can see we have more lower mass things than high mass things, which is expected. There are more low mass stars than high mass stars. But there's some structure in this. There's a peak maybe around about 35 solar masses, maybe some additional peaks and troughs at lower masses as well. So this encodes information about the astrophysics of the sources. So this tells us all sorts of interesting things about the properties of the population of binary stars that go on to form merging black hole and neutron star binaries. Okay, in addition to looking at the intrinsic population of black holes, we can look at populations of our universe itself. We can look at measuring the expansion of the universe. Here we have a plot doing this. This is a combination of using GW170817, which was a binary neutron star merger for which we have an electromagnetic counterpart. So we know exactly its source there. From the gravitational waves, we get the luminosity distance. From the galaxy where the source is, we get the redshift. Putting those together, we can get the Hubble constant. We can do something similar with the other candidates. There we don't know the host galaxy exactly, but we can use galaxy catalogs to do this probabilistically. And that overall gives us a distribution, probability distributions for the Hubble constant, which is not yet comparable to other means, but the uncertainties will shrink as the population grows, and particularly if we get any more with electromagnetic counterparts. So we have astrophysics, we have cosmology, we also potentially have fundamental physics. Here's a plot from our paper looking at consistency with predictions of general relativity. We can do many different tests looking for potential deviations in the waveform. This particular plot here is showing consistency of masses and spins inferred from the early in-spiral part of the waveform with the late merge and ring down part. If everything works according to GR, we'd expect this to be at 0, 0. And when we stack all our observations together, we see that it is still consistent with that. So no deviations yet shown up there. So we potentially have a way of testing strong field gravity here that we wouldn't have in any other way. So lots of exciting science. We have lots of data coming in. Hopefully you're all excited for the rest of this program. In this talk, I'd like to start by just giving a bit more of an overview into our discoveries to date and the range of science that we can do with that. Then go into a bit more of the data analysis, how we infer the source properties of these systems, and end by looking at where we're going to be in the next couple of years. Okay, so let's start taking a look at these discoveries. Here's our population of binaries to date. What can we learn from these? And now I'm just going to concentrate on the individual systems because we're going to have talks later in the program, so we'll look more at the ensemble of all of them. So why are we interested in these is, well, we know that most stars in our universe are binary stars or higher multiples, and so we really like to understand the physics of everything that goes in here. Potentially looking at their stellar remains, we can work backwards to understand the physics of how they got there. Now, the processes of how you actually end up with a merging binary is really quite complicated. There are many potential ways of doing this. Here are perhaps two of the best known. On the left, we have a cartoon showing the evolution of an isolated binary, so two stars that live their lives together that end up as a merging black hole. Go through various phases here. As they get older, they puff up, they transfer mass from one to the other. We have supernova explosions as stars collapse down. Potentially we have mass being transferred from the second star back onto the first one. And if that's fast enough, we can get a common envelope forming where we have the black hole and the core orbiting inside this envelope, which helps shrink down the orbits to get them close enough to merge. We have a second black supernova here to leave them together. So there's a lot of physics which can be changed here, the efficiency of mass transfer, the magnitude of supernova kicks, which can affect this channel, which is currently uncertain about the precise details of these, and will leave imprints on things like the masses of the black holes, and also things like the spins. So the spins could be affected by how big the supernova kicks are, because that tilts the orbit, so that will change the orientation of the spins. Potentially things like how efficient angular momentum transfer is within the star will impact the magnitude of the spin. So when a star puffs up, if the outer layers are strongly coupled to the core, as it puffs up, the whole thing will slow down, leading to lower black hole spins, where if the core is decoupled from the envelope, then it can maybe spin a bit faster. On this side, we have dynamical formation. So here we don't require that the star lives its life with a partner without blowing itself apart or merging together earlier. But we say if we're in a dense environment like a globular cluster, every so often we're going to have a dynamical interaction that gets close enough together to allow us to form a binary or swap out a component of the binary to get a new one. That will often select preferentially the heavier objects, and glancing interactions will harden the binary, make it shorter, shrink it, so we can bring things closer together to merge. Again, there's all sorts of physical uncertainties here. The density of the cluster, which goes into these, as well as some of the stellar evolution properties, not so much things like mass transfer, but stellar winds, which in both cases will impact how much mass a star loses before it collapses down, which will affect the mass of black holes. And that the spins can also have a subtle effect here, that if we have black holes with high spins, when they merge together, they get a large gravitational wave recoil kick, which can potentially eject you from a cluster. Whereas if you have smaller spins, the kick will be lesser. So potentially you could stick around inside your cluster and have a second go at forming a binary. So this might be a way of getting hierarchical mergers if you had smaller spins, depending on your environment. So we want to uncover all of this from looking at our observations. And from them to date, we see we have this range of masses. Most of this is consistent with our observations to date, but we do have some notable higher and low mass ends. Of particular interest, you might note here we have this region where we're not so sure if we have neutron stars or black holes. We don't know yet exactly what the maximum neutron star mass is, so this is something we would like to measure. Unfortunately, to date, we don't have good measurements of the systems themselves to confirm if they're being tidally distorted. So we can't tell from the gravitational wave signal alone if they're neutron stars or black holes, but we have a number of systems that are potentially in the range of masses where they could be either. So we know, there's systems in this range, and but we don't know what they are yet. So this will require currently some physics input, but maybe in the future we'll get tidal observations that will tell us about whether these systems are one or the other. Okay, now, coming back here, if we zoom in at this region again, you can see that we seem to have pretty much continuous distribution of masses in the gravitational wave case, but there's a lack of observations electromagnetically. This was proposed as being a mass gap between neutron stars and black holes based on X-ray observations, which would tell us something about supernova explosions. But it doesn't seem like we have that from the gravitational wave case, at least not to the same degree. You can also see that we have masses that extend far above the electromagnetic case in the gravitational wave case. Part of this is selection effects. Gravitational waves preferentially see things higher masses. Part of this will be the systems that we can observe with X-rays. We're really looking at our our local neighborhood where we have higher metallicity stars, which lose more mass, whereas with gravitational waves, we can look further back in time to see low metallicity stars that lose less mass and have higher mass black holes. But there's more to the story than just that. Here we have a plot from that shows the relationship between initial mass of a star and the mass of the remnant that it leaves behind under different circumstances. This is just for an isolated star, so ignoring binary interactions for now. The different colour lines reflect different metallicities of the star. As you get to higher metallicity, going from lower metallicity, you can see because of stellar winds, you end up with lower mass black holes. You lose more mass as you start at the same initial mass. You can also see there are a couple of mass gaps in these plots where no black holes were predicted to form. There's one mass gap here at the lower end between neutron stars and black holes in this plot, but no gap here. These are two different supernova models that say how stars explode and how much fallback you get. This model was proposed to explain the mass gap from X-ray observations. Since we now see some gravitational wave systems in this gap, we can perhaps say that this model is ruled out. And we need something more like this, although not necessarily exactly like this, and we still need some way of explaining the X-ray observations. But in both models, we see that there's a gap also at higher masses, around about 45 or so solar masses up. This is the pair instability supernova mass gap. The idea here is that the cores get so massive that you get photons being converted to positron-electron pairs. This is very bad news when you're radiation supported, because you lose your radiation, star collapses down, heats up, get runaway thermonuclear explosions, which disrupt your star. So we should have no black holes here. However, we do seem to have black holes in this range, so we need something else going on. Perhaps it's some correction to the physics of the stars modeling here. Perhaps we have mergers, these hierarchical mergers of black holes going around again. Maybe it's mergers of stars where we have stars merging together so the core can be small enough to avoid the pair instability, but we have an extra envelope of stuff that can collapse down onto the black hole to make it more massive later on. We have uncovered a range of masses of black holes. There's a whole host of physics that can be encoded in these sources. We have a range of masses going from neutron stars up to black holes. We're not sure where the divide is. We're not sure of the physics that's encoded in these yet. But as we start building up the idea of the population, we can start digging into certain physics of these formation channels. What fraction comes from isolated evolution? How does mass transfer work? How does supernova work? What's going on with the mass gaps, if there's any additional physics that we're missing. All of this relies on understanding the property of our black holes. What are the masses and the spins? So how do we do this data analysis? What we want is the probability of having some parameters, here denoted by theta, so masses, spins, distance, things like this, given our data. So to calculate this, we use Bayes' theorem. We start off with a prior. What is the probability of our parameters before we see the data? In all our Ligo Virgo Kavli results, we tend to use a relatively uninformed prior, a prior that's easy to divide out, so that when you're doing your interpretation, you can divide out this prior and put in the prior that you want to describe the system. We have the evidence on the bottom. This is useful for model comparison. For our purposes, will be a normalization constant, so I won't talk about it too much. The final piece here is the evidence, the probability of the data given the parameters. This is where the important stuff for the purposes of this talk is encoded. So let's take a look at what this is. In effect, it's just a fancy normal distribution. We say that at each frequency, we have a system where the noise is described as a zero mean Gaussian, so we're equally likely to have positive and negative fluctuations, and the magnitude of the fluctuation is set by the noise in the detector at that frequency, the power spectral density. We encode this, or amplitude spectral density for the standard deviation, power spectral density for the variance. So at each frequency, we take a look at what we think the signal should look like, subtract out our data. The remainder should be noise. That should just be our zero mean Gaussian. So dividing out by the Gaussian of that will give us the probability of having the signal at this a particular frequency, add up all the different frequencies, that gives us the overall likelihood. Our model for what the signal looks like is a prediction for the waveform, and then we add in a little bit of calibration inaccuracy for our detectors, so assuming we've not quite mapped between gravitational wave strain and the output of our photodiode perfectly. Currently, we add in an amplitude factor and a phase factor with a spline model. Potentially something more physical can be done in the future, but factoring this all together, we have our model for the likelihood. Now, this relies on a few assumptions. It will rely on us having an accurate model for the waveform, which we'll come back to a bit later, but it does also rely on this assumption that the noise is nice and Gaussian quite heavily. And unfortunately, we know that this is not always the case. I'll come back to that in a second. So if you remember earlier, I showed you the plots of 1509-14, where we had a look at the simple plots, just how we can do things by eye, which I told you is not how we actually analyze the data. Now I've explained a little bit about the noise weighting. I can show you a plot which shows about how we actually do our data analysis. So here is the data that has been whitened, so divided out by the noise spectral density to give us an idea of what the fluctuation should be, and then transformed back to the time domain to give you an idea of what the fluctuations are. It looks maybe a bit smoother in this case here. So this is what we really put into our analysis. Okay, so that is assuming all the noise is nice and Gaussian. We know that's not the case. Here's perhaps the most famous example of GW17817. Here's a time frequency plot of the data. And if you look, you can see here is the chirp of the gravitational wave signal, which is actually a very beautiful chirp that you can actually see it by eye. On top of this is this huge glitch, which prevented us from analyzing it because it definitely violates our assumption that the noise is nice and Gaussian. So we had to subtract this out using a particular glitch model. In this case, it was quite nice and simple because this is a very simple glitch, but this is not always the case. In 03 in particular, we were affected by a large number of glitches due to light scattering in the detector. So this is light bouncing off something it shouldn't do, get reflecting back into the optics of the system. If the thing that it's reflecting off moves about at all, that introduces a frequency modulation. So we had lots of scattered light, which often shows up as arches that we needed to remove from our data before we could analyze it under the assumption of Gaussian noise. Okay, so assuming we do have nice Gaussian noise, we have a spectral density that will look something like this curve here. The lower the curve, the less noise we have at a particular frequency. We then have our signals here. Here's an example from our observations of 3 signals from 01. And we have where the signal is higher than the noise curve, that's where we have higher signal to noise ratio, that's where we get more information from our inferences. So let's have a look at our first 3 detections, 1509-14, now GW 1510-12, originally called LVT, 1510-12 is its lower significance, and GW 1512-26. Looking at these, you can see there are differences in the gravitational wave signal. We have 1509-14 is louder. That comes from it being higher mass, and it also tells us something about its distance. And you can see it merges at lower frequencies than the other. Lower frequencies corresponds to higher masses, bigger black holes, merges where the orbit is still wider, so that corresponds to lower frequencies. You can see we have lots of information from the merger and ring down part of the waveform. That's this part roughly in the frequency domain. So from this we can measure parameters that influence the merger and ring down quite nicely. So total mass, spin of the final black hole mostly comes from the spin of the line components of the spins. It's measured quite nicely here. We take a look at 1512-26. You see this merges at much higher frequencies. That's going to be a lower mass system as it merges at higher frequencies, smaller black holes, and we get much more of the in-spiral in band. We see many more cycles here. So this means that we'll be able to measure more accurately parameters that control the in-spiral, so principally the chirp mass, a particular combination of the 2 component masses that tells us how quickly it spirals together, and next order be the mass ratio and the aligned components of the spins again. that control how quickly it inspires. So that's what we measure best. So we put our data in, we compare it to waveforms, we infer the posterior probability of the parameters given the data. That results in plots like this that show the probability distribution for the different sources. So here we have 50% and 90% contours with our default prior for these three systems. You can see 150914, lower frequency system, higher mass system up here, 151226.
Christopher, sorry to interrupt, you have 5 minutes.
5 minutes, okay. Thanks. Lower masses, and you can see here we have a banana shape, which basically traces out a line of constant chirp mass. So we have a degeneracy along that direction. Okay, so that's the status of things after O1 when we do our inferences. Here we have things after O2. We're starting to fill in this plane a lot more. We also have our first binary neutron star observation, GW7917. This is much lower mass. We have a much longer inspiral. So this plot actually greatly exaggerates our uncertainty on the masses here. The line should actually be much, much thinner because we measured the chirp mass so beautifully. We continue up now to O3. Here are results from O3A. We've switched the plotting now to total mass and mass ratio. You can see most of our systems, most of our observations are in this mass range here, around about 30 plus 30 solar mass black holes, mostly consistent with equal mass. But we do have now a few systems that start to disagree with some unequal mass ones. Here's GW190814, which could potentially be a neutron star black hole system. We also have some much more massive systems. This is important for understanding astrophysics, but is also important for the waveforms. When we have high mass systems, unequal mass systems, we need to have gravitational waveforms that include higher order multiple moments in order to accurately measure these parameters. So we need to have these in as well. We come now to O3b, second half of the third observing run, changing the plotting style again, excuse me, to make the plotting a bit more easy to see for these extremely mass rate, comparatively extreme mass ratio systems. These are again very important for the higher order multiples, and these are this event here, 191219, is particularly uncertain in its parameters because this is now outside the range at which we would typically use our waveforms. It's outside the range against they're calibrated against numerical relativity. So we're starting to really hit the limits of what we can do with our waveforms. You can also see we have some very large uncertainties from the very quiet systems. We have more high mass systems. We have more unequal mass systems. So we really have a range of masses going on. Let's take a quick look at the spins of these systems. Here's a plot which shows probability distribution of the spins. These plots are constructed so that if we get our prior distribution back, we get a uniform disk as shown on this half. And if we get something measurable, we'll get darker where it's more probable and white where it's less probable. Now this plot here is for GW190814, which is this unequal mass system. And you can see here's a particularly nice example of the fact that we can measure the spin of the primary. That's the spin shown on this half of the plot. And we can't get the spin of the secondary because due to the mass ratio, the primary affects the spin dynamics, but the secondary does not so much. So we get some quite tight constraints on the spin magnitude. That's the radius direction here for the primary. It's constrained to be quite close to 0. Normally, we often get constraints of the aligned components of the spin. So if we're in this direction, we're aligned with the orbitangular momentum. This direction, we're anti-aligned. And if this direction would be in the orbital plane. Normally, we get the aligned spins because that's what controls the inspiral, what goes into the principal components of the final spin. But here we also get some constraints on the fact that it's not large and in the plane. So this is what would affect the precessional dynamics. There's spins precessing. Precession is more important for these type of unequal mass systems. And in this case, the fact that we can't see precession in the signal means that the system can't have large components of spin. If it did, we'd see that in the signal and we don't. So we do manage to constrain this to be quite small overall. So this is a beautiful example. This is perhaps our best example of measuring spins. In general, most of our spins are just kind of consistent with 0 for both its components. So in this plot, I've compiled a few interesting examples of atypical systems, so systems which aren't just consistent with 2 0 spins, and not be able to say much more. In the top row are 3 systems with comparatively unequal masses, so things which could potentially be neutron star black holes. Each of these cases, you can see, you can't really measure the secondary, but we can the primary, and in each case, it's consistent with 0 and is consistent with, so not just in the spin aligned with the orbital angular momentum, but with the spin in the orbital plane is consistent with that being small. While most of our black holes...
Christopher, you may want to wrap up.
Yep, 2 minutes. In this case here, we have most of them being consistent with 0, but we have here some cases where the spins are non-zero. So we have a couple of cases where the spins are consistent with being small, potentially here being aligned as well. We have one case here where the spin's quite high, consistent with X-ray observations of large spins. This is quite a low significance event, so maybe it's not the one to be most confident in, but if real, comes out with very large spins. Final row here are cases where we have spins which are misaligned with the orbital angular momentum. 1911-09, where the spin is anti-aligned. 1912-15, where we have some preference for spin in the plane, and 2001-29, which is the strongest evidence for precession, yet we have a clear preference for spin being in the orbital plane here. So we have a range of mass and spin measurements. Okay, so let me just quickly skip over the future. Our current network, we have LIGO and Virgo online. CAGRA started observing just after the main part of 03 ended. It did a short observing run with GEO, which has now been published, no detections yet from that. But for 04, we'll be joining more fully. And then towards the end of the decade, we'll have LIGO India as well. So here's a current timeline for when we're due to start observing again, which is at the end of 2022, which should have the 4 detectors, 2 LIGO and Virgo online. The sensitivity of detectors will be upgraded. Here's the binary neutron star range and average range we can detect binary neutron stars. Larger range means detecting things further away, means more detections, and it also means higher signal to noise ratio. So higher signal to noise ratio means that waveform systematics are more important. Here's a plot that shows how important different systematics are as a function of signal to noise ratio. And basically, at the end of 05, we'll be around here, where our current waveforms are really at their limits. When we get to third generation detectors, then we're really at numerical relativity being at its limits currently. Okay, so let me wrap up now. We've seen a range of neutron star and black hole observations. These are great for all sorts of science. Inferring the properties of these signals requires understanding our detectors, calibration, noise, as well as the signals. We need things like precession and higher order modes included in there. In order to analyze these signals, we need fast waveforms because we have so many signals that we need to analyze. They need to be reliable across a range of parameters because we have so many unusual systems, so many systems which cover a range of parameters. And they need to be accurate because any biases here will affect the downstream physics, and also because as signal to noise ratios increase, even small uncertainties can become more and more significant. So thank you very much. I'll leave you with my conclusions and links to sources for more information.
Okay, thank you very much, Christopher, for this very nice talk. So we now take questions. So you can write your question on the chat. Sorry, you can either raise your hand if you are on Zoom. Of course, raise your hand also in the room. Donald is following that. Yeah, so let's see where we take the first question, whether on Zoom or from the room. I see Satya has a question.
Thanks, Alexandra. Christopher, wonderful summary as usual. Great to hear. One of the questions I wanted to ask was a very specific one, which is about the model that you showed, which predicts the population with gaps and without gaps. You didn't have the slide numbers, I couldn't write it down quickly. It's earlier in the thing. Now, my question was, did it include multiple mergers? Yeah, this graph. Did it include hierarchical mergers in this?
No, so this is just the single stars, so no binary interaction, so no mass transfer. and no things like hierarchical mergers. And the reason I've neglected that is just because this plot is to keep things simple, that you only have a one-to-one mapping between initial stellar mass and final black hole mass if you have an isolated star. As soon as you introduce a binary companion, you need to have extra plots which shows, which compares the mass of your companion, how far away you are from your companion. So it complicates things and fuzzes things out much more.
Yeah, especially since you mentioned the mass cap, I wanted to understand that. Okay, now my general question was about, what do you think are the biggest questions raised by the observations so far? Is it the race, is it the population, and so on? Yeah.
That's an excellent question. I suspect this is what Ilya is going to touch on later in his talk. So I think this plot highlights things quite nicely in terms of the physics of just looking at individual systems. So one is what's going on with the systems in this mass gap, the upper mass gap, the parent-Olympic mass gap. Is this due to mergers or some other extra physics that's not going on? And I think the case is there are plenty of predictions now for how you can form systems in this mass gap. But the question is, can they form enough systems? And can they form enough systems here while being consistent with the number of systems they're forming at the more regular masses? So can you get the balance there quite right? Some of the high mass systems like 1905-21, the 1904-03 system I showed with the spins are really quite difficult to form in any model. So how do we get those? And then the second thing is the systems in this lower mass gap here. So the existence of objects, again, in this lower mass gap is fine if you throw away these models that were designed to explain the X-ray observations. We need to find a new way to explain the X-ray observations, but that could be due to some selection effect, when a binary is X-ray right and things like that. So the masses here I'm not so concerned about, but the mass ratios I think is interesting. Because forming the systems with merging systems with these mass ratios at the rates that we're seeing given our observations is quite difficult, I think. So that I think potentially holds some key physics there.
Christopher, this is Lars Biltzen. I have a question for you from the audience. So can you go back to your future slide? I'm curious to have you comment on two aspects of the upcoming runs. So the first question is for LIGO Virgo. You showed January 2023. Can you give us a confidence number for that being the actual start date?
Yeah, so I think it's December this year is the nominal start date. So as I work on data analysis, they never let me touch the detectors, which is the right call. So yeah, I will not give a confidence interval on that. We have pushed back the timeline somewhat due to COVID and things going on. We have slowed the work down. I know that currently people are looking at noise hunting, which is a good sign in terms of making things. But yeah,
okay. Then my second question is, can you give us a sense, given the ranges for LIGO and Virgo, can you give us a sense of the added value of CAGRA? Because I'm struggling to see the added value that CAGRA brings relative to the other two. Can you help us understand that?
Yeah. So this is an excellent question, and I think the point is, at these current sensitivities, we would not expect there to be a detection which involves all 4 detectors, unless there was, say, a galactic supernova or something like that, which of course would be fantastic, but is unlikely. The value of CAGRA really, of course, comes when it reaches its higher sensitivity. So it's a detector running for its first time. It's going to take a while to get up to that speed, but when it hits 05, then it can really start contributing to things. And that really comes in, I think, for the sky localization is really important, and the distance localization. And the point here is not so much just that you have going from 3 detectors to 4 detectors that improves sky localization, that shrinks your uncertainties, but it's more the fact that at any given moment, you have at least 3 detectors online. So if you have 2 detectors online, you can really just find yourself on some kind of band on the sky. With 3 detectors, you get down to a single blob. So when you have these more detectors online, you get a higher fraction of time where at least 3 detectors are online, which improves your source localization, great for follow-up activities then. And it will also enable extra science, such as for testing the polarization of the gravitational wave signals. You need more detectors to rule out all the various combinations of polarizations. So
Chris,
those
sorry, this is Luis Lehner, also from the audience. Piggybacking on Lars' question, can you say something about the plans for early warning, perhaps messages, and what type of information will be communicated to the community?
That's a good question. So I don't think the plans have been completely formalized about exactly what's going to be sent out yet. This web page here is actually the place to check out for official announcements on these things. Because things are scaling up so much compared to 03, I think there will be a few changes. Maybe the big picture will be the same in terms of alerts going out to the public, they'll be to the community. They will include things like localizations, which will be updated if the analysis is refined on a very short timescale. It will include information such as, we think this is maybe a binary neutron star or a binary black hole based on the preliminary analysis we have. One of the big things people are trying to do is actually get early warning, by which I mean detection of candidates before merger being sent out. So trying to save every second possible on these mergers. As you increase the low frequency sensitivity of detectors, you get more inspired. That maybe becomes more popular. So you may see updates along the lines of, there's something which might be merging, and then a quick update as we get more SNRs, the signal comes out. The infrastructure for all this, I believe, is still being developed. So I don't want to say anything more about specifics there. I don't know if there's anyone in the audience who's maybe more involved in that than I am who could say.
I would like to ask you a question. So you showed the plots of the distribution of masses. And of course, you commented that they depend on selection biases, but also the population studies and so on. And I would like to ask you if you think if there are some predictions of how this plot might change with third generation detectors like Einstein telescope or Cosmic Explorer. And I ask this because I guess that these detectors will have sensitivity in lower frequencies, and we might see probably higher mass systems. So I would like to ask you if there are some predictions of how this plot change.
Yes, let me go through my bonus slides right to the end here. So a couple of plots here which make this point about what you can see as you improve sensitivity compared to sort of 05 sensitivity. And how far you can see with sort of a factor of 10 increase shown in blue compared to what you get with Einstein telescope or Cosmic Explorer, which are these white lines here. So I think the things to really note here is, you can get down to lower masses as you have improved higher masses, lower frequency sensitivity here, which is really good. But the main thing I'd say is the number of sources and the redshift distribution. And why this is really important is that the population you see, actually at which you can infer that really good scales with the square root of the number of sources. So in this plot shows as compared to a boost compared to sort of 05-ish sensitivity, how many detections you can see per a redshift bin. Okay, so you can see that with a factor of 10 increase, you can get something like 500 detections, maybe 1,000 detections, depending on exactly how many systems are. The different colored lines are different bins, the dotted and dashed lines are based on rates, how far we can see. So you're seeing hundreds of systems, at least per year, per redshift bin, which means you can do the current inference we're doing with LIGO and Virgo to infer the mass distribution as a function of redshift, and really see how this distribution changes over the history of the universe. So I think the real key thing from the third generation detectors will be getting the mass distribution and seeing how it evolves across the universe. So then you can see how the astrophysics change, how metallicity, how changes in environments impacts the distribution.
Okay, thank you.
Okay, so in order to remain time, so let's thank now Christopher.